Hi, thanks for joining our webinar today titled Particle Agglomeration, a technical how-to guide with illustrative examples, given by our speaker, Dr. Willie Hendrickson. Willie is the founder and CEO of AVEKA Group, one of our most popular and regular speakers at the HORIBA webinar program. So based on the number of registrants I saw just a few minutes ago, looks like agglomeration is a very hot topic and probably a shared pain point for many of us people in the particle characterization field. So I definitely look forward to what Willie has to say and share and get to our Q&A at the end of the session. I'm going to pass the ball to you, Willie.
All right. Well, thank you everybody for joining us today. This is it's always a pleasure for me to give these talks, and hopefully you find what I have to say worthwhile. We're going to talk about agglomeration today, a technical how-to guide with illustrative examples. And let's get right into it and see if we can get through this and still have time for questions. So the outline is I'm going to give you a one-slide overview of AVEKA just to let you know who we are. I'm going to talk about what I consider the big six of particle processing, some dilemmas in particle processing, agglomeration methods, some examples, and then we'll close up with some opportunities of where you can get more information and some conclusions on why this is important. So let's get into it, and thank you again for listening to me. AVEKA itself, if you don't know, we're a contract manufacturing company focused on particle processing. We were founded in 1994 when I left 3M and took a pilot plant and made it into the company. Recently, 4 years ago now, we became an ESOP, an employee-owned and operated company. We have 5 manufacturing plants and 290 employees. So we see a lot of different requests on particle processing, and actually agglomeration is one of the ones that we see quite a bit of interest in. So this is what I call the particle processing, the big six. I think everybody can have their own list of what they think is important in particle processing. I put characterization up at the top, not because I'm trying to play to our host HORIBA, but because I truly believe if you're not characterizing what you're doing, how the heck do you know that you're doing the right things in particle processing? It's hard enough as it is, and we need to understand what's going on. I think the other processes or areas that are very, very important for all of us in particle processing is flow, size reduction, drying, agglomeration I have on there because this is what we're going to talk about, and particle coating. Some of you might feel that crystallization is important. Some of you might have other areas. These are my big six. If you're really going to be a particle processing person, you need to have a little bit of understanding in each one of these, and probably even a lot of understanding in each one of these. Now, having said that, particle processing, I think if you are in particle processing, it's one of the toughest areas to be in. It's not chemistry, it's not engineering, it's a little bit of material science, a little bit of chemistry, a little bit of engineering, and we have these issues that are just difficult. So when you're starting in the lab, you're picking a process to actually do whatever you're doing, drying or agglomeration or whatever. And you know something? We are always limited on what you have, unless you're really lucky and you have one of everything in the world. I come close to that, but we still have to make choices. And when you make a choice, you kind of set the trail for the rest of your project. And it's hard to change from a grinding process or a drying process to something different when you find out that you didn't choose exactly the right thing. The other thing that we deal with is scaling up. Scaling up in general with liquids and solids, or liquids and gases, has some challenges, but scaling up with solids processing is extraordinarily difficult. I have an example here. Somebody is doing a distillation in the lab, and boy, that's a nice little setup that you have there, but it doesn't look anything like what industrial distillation looks like. So just understanding what sort of steps you're going through in that scale up and volume are a very big thing to understand when you start. Powder flow, I don't think we can say enough about how much of a challenge powder flow is to us. I don't have a picture of it. I should have put it on here. You know what hammer rash is. I mean, those of us that work in plants know exactly what hammer rash is, where the operators go and pound the pipes until the pipes are dented because the powder gets stuck there. Powder flow can be one of the biggest issues that we have. And interesting for today is obviously agglomeration. With good agglomeration, you can improve your powder flow, and we'll talk about that a little bit. And finally, functionality. As we go through all these things, you know, we are taking a powder and we're trying to give it some functional characteristics, and agglomeration is one of these processes that is really all about functionality, which we'll talk about. Now, as we're doing this, basically, particularly when we're agglomerating, we are making engineered particles. You know, and these engineered particles are, you know, not just something that you pick up off the ground, you know, the sand, the dust, or whatever. We've controlled the size. We've made it multi-component. We control that functional property. We are controlling the structure of the complex structure or shape. Lots of other things that we're doing here. Agglomeration is really one of the key points in engineered particles. You're taking that particle that you made and now you're functionalizing it, you're engineering it to give you that final result that you need. That shouldn't be that hard, but you know, I think those of us that are in this area know that, wow, this can be part of the real challenge that we're looking at. So let's look at some uses of agglomerated materials. And the bottom line, I have three pictures here. I have a picture of laundry detergent, I have a picture of yeast, and I have a picture of tablets, pharmaceutical tablets. Those three bottom structures that are there, those materials, are ones that we are probably dealing with in an everyday basis. I wash my clothes, I bake bread at home. As I've gotten older, I'm taking more and more pills. And each of those, a pill itself is an agglomerate, but to actually make the capsules and tablets, there's a lot of agglomeration that goes into that. One of the uses of agglomerated materials that you might be less knowledgeable about or less knowing about is the one I have up at the top. And I have three pictures up here. Let's look at the middle picture. This is a picture of an agglomerated iron oxide, and this is what's used in blast furnaces nowadays. Those particles, those agglomerates, those balls, those granules, whatever you want to call them, are about 3/8 of an inch in diameter. They can be a little bit bigger, a little bit smaller, but you know, kind of in that size range. Basically, the reason that people are spending an extra time in taking iron oxide, iron ore, and agglomerating it before it goes into a furnace has to do with some history here in Minnesota, where I'm from. In the 1880s, it was found that there was a huge deposit of iron ore in northern Minnesota. And in fact, at the time, I think it was one of the largest iron ore deposits in the world. And it was great iron oxide. It was highly pure. It was 100% iron oxide. So you could just dig it up out of the ground, put it on a boat, ship it to Pittsburgh, and you could make iron in a blast furnace. Well, for 50 years they did this, from about 1880 to about 1930. And about 1930, they realized, you know something, we're going to run out of this high-grade iron ore sometime in the mid-60s. And so somebody at the University of Minnesota, I don't remember the name, I apologize, took it upon themselves to take a look at the low-grade iron ore that was up in Minnesota, and that had an amount of low-grade iron ore that could last us for 600 years. But instead of it being 100% iron oxide, it was only 30% iron oxide. So they had a project. They dug up some of this taconite ore. They ground it up. They beneficiated it. They separated out the sand and the silica and all the other stuff, the alumina, out of that system. And they ended up with this beautiful 100% iron oxide, again, about 10 to 25 microns. And they shipped a whole bunch of that off to a blast furnace, and they put it in there, and the blast furnace immediately shut down. Now, what they were digging up is these big chunks and granules and putting them in a blast furnace. It worked just fine. They put in this purified material, and because the particle size was so low, you couldn't force CO through the system and reduce the iron. And so they went back to the drawing board, and they actually granulated the iron and made these pellets. In Minnesota, we call them taconite pellets. I think the rest of the world uses this now, and they'll just call them iron ore pellets. The process for agglomerating, you can see on the left side of the screen, it's a drum granulation process where you take the wet cake that comes out of the wet ball milling and filtration process into a tumbling a drum, and you actually come out with these particles out the end. They fire them, and the picture on the right is the amount of iron ore pellets they produce. What you're seeing there, they actually produce 1,000 tons, 2 million pounds of iron ore pellets an hour. Yes, actually an hour. It's an incredible amount of material. So this is one of these big volume agglomeration processes. And I just want to leave you with a little bit other how important the functionality of getting this size right so they could get the CO2 through, the CO through, I'm sorry. What happened is when they put these iron ore pellets in there, the blast furnaces operated different. They operated 5 times faster because the agglomerate allowed better flow of the carbon monoxide through the system. 80% of the blast furnaces in the United States closed down. This is a place where particle science really helped, and from a sociological aspect, it was a little hard on people. Well, let's take a look at, obviously the functionality to have a better airflow through a system is one thing, but many of the issues that people use agglomerates for is dedusting, the powder flow that I talked about earlier, density control, wettability, compositional uniformity, tableting, and clearly powder flow, compositional uniformity, and tableting. These are all really key to pharmaceutical processing, but the wettability, the density control, even the compositional uniformity are important for just about every aspect of particle processing in the agglomeration and particle processing. Let's see, so let's take a look. How do we actually go about this? And this is a very generic 5-step process. You got to have your right particles to start with. You're going to add some water or binder to the system. You're going to go through some process that you're actually going to cause the agglomerate to form. It's a fluid bed or a high shear mixer or something like that. You're going to dry the particles, and finally you're going to package them or use them. From my standpoint, this is only 3 steps. What can go wrong on something like this? The answer is, and you all should be laughing right now, the answer is just about everything. This all has to do with the process of how fast do you add the water. You add it too fast, you're going to have a mess. If you add it too slow, you're not going to get agglomerates. If your starting material is inconsistent, we've actually had a case, I'm not going to talk about it today, that we went from one material change from one vendor to another. It completely changed the entire functionality of the product that came out at the end. You can end up with agglomerates that are too weak. I'm going to talk about that because this is a big issue on this. You go through all the trouble of making this, and then it's not strong enough to actually use. We can get the wrong structure, and I'll talk about this a little bit, what kind of structures we actually get. The particle could be too dry, the functional characteristics could be wrong. And in fact, even after you've gone to all the trouble to find out the exact process parameters that you want, whether it's a fluid bed or a high shear granulator, whatever it is, a change can happen. The humidity in your plant can change, the operator can turn something down or up, the air pressure in your line can change, and all of a sudden you don't have the product that you're having, that you're looking for. Even when you get it right, everything can go wrong on this. Of course, this is what particle processing is all about in any case. And how do we actually get control of this and understand it? Hopefully, I'm going to give you some ideas of where to go with this. So let's look at some of the agglomeration techniques that we might be looking at here. High shear agglomeration, it's down in the lower left-hand corner here, lower right-hand corner, excuse me. This is a Forsberg mixer or a Bella mixer, and we will actually use this as an example in a couple of our examples in a little bit. In this case, the particle formation process is done by these paddles moving very, very fast. You're adding binder to the system, and you're going to form your granules. One of the processes that people use an awful lot is fluid bed agglomeration, shown over here on the left side of the screen. In this particular case, there's a fluidized bed. You're fluidizing the particles, you're spraying into it. There's a drying process that goes in there, and out comes your material. You know, I like extrusion agglomeration. That's the twin dome extruder shown down here at the bottom, where you're actually taking a wet cake and using an extruder to push it through a screen or a die, and you're making noodles that you can then dry, and you have an agglomeration process. There's advantages to that. Obviously, I'm showing the drum granulation process, and this is the iron ore process here again. And finally, up at the top, there's a number of tableting or pressure processes like chalcination or shugi that you can actually make agglomerates also. So there's more options than this. I'm just giving you some options, and we'll talk about 2 or 3 of these during the course of the talk, and try to get us to, you know, what's the best one to choose and what are some of the best process conditions to use. You know, I can't hardly talk about agglomeration without talking about drying. And you know, this is my standard. You know, what kind of drying techniques are there for particle processing? You know, from spray dryers to roll dryers to, you know, tray dryers to drying out in the open to flash dryers and fluid beds in there. You know, the problem is that with all these drying techniques, in general, most of us for agglomeration are using either a turbulized or a high shear type of dryer, like up in the upper left-hand corner, or fluid beds in the bottom. So even though lots of drying techniques available, we're kind of pushed into, you know, some of these other ones. I'm sure flash dryers can be used and tray dryers can be used, but realistically, fluid beds and turbulizer type of dryers are going to be the dryers that most people are going to use. So let's just talk about, you know, what makes a fluid bed. Why would we want to use a fluid bed? And what are the structures of these particles, and what are we really looking here? So the nice thing about a fluid bed is that you can do 3 steps in it. You can add liquid, you can do the agglomeration step with the fluidization process, and you can dry. Now, the interesting thing about fluid bed processing is how you add the liquid, where you add the liquid, how fast you add the liquid will decide whether you're getting an agglomerate, you're getting just a big gooey mess inside your system, or you're actually coating the particles. When we're trying to do agglomeration, we don't want to do what we're doing down here on the bottom, this spray coating. I mean, if you want to do spray coating, the fluid beds will work for you. But when we're doing agglomerates, we really want to make this structure that's over here. So let's just take a look at it from a fundamental few steps that we're going through here. We've got our powder that's fluidized in our system. We're going to start adding droplets of water to this system. So obviously, if we add the droplets too big or too fast, it's going to be a different end game. What we're really trying to do is we're trying to get liquid bridges. So we're trying to get that water dispersion. We're trying to draw these particles together and eventually dry them, either because there's a binder in there or some of the particle actually dries to form these solid bridges. And we're actually looking for some sort of structure, call it a blackberry structure or call it a cluster grape structure. This is what we're looking for. Most of the characteristics that we're looking for. I'll give you some examples where that's not what we're looking for, but you know, from a flowability, from a wettability, you know, we're looking for this sort of structure. Now, if you look up at the top here and you see that the spray nozzle in this schematic is shown up at the top, you can put your spray nozzle in a fluid bed dryer in a granulation system, a high shear granulation system, just about anywhere. But the reality is the best place to put it is smack in the middle of your fluidized bed, because when you spray, you want that liquid not to hit the walls, but you want it to hit the particles to start forming this structure that you're actually looking for. So if your fluid bed isn't operating right, if your atomization is not operating right, if all these things can have an effect, and pretty soon you cannot have the agglomeration process that you're looking for. But what we're going to be looking for, and most of it, is we're going to be looking for this grape cluster structure is what we're going for. Now, this is the background. This what I want to do is I want to switch to some of the examples I have so we can actually talk about, you know, how the process and the parameters that we're using here. And remember, I said This is this can be very, very difficult. It can be very, very hard to do unless you're a cat. Now, you know, as much as I said how hard it was, how is it that cats can make these nice clusters every single time they use a kitty litter box? The reality is that we highly engineered this particle to make it easy, so even a cat can make it work every time. And it does work every time. But if we're not as lucky as a cat to have somebody give us the perfect particles to do in the best possible way, we're going to have some other challenges. So let's look at some of these examples that I want to look at. We're going to look at 3 processes. We're going to look at some extrusion agglomeration examples. We're going to look at one high shear agglomeration example, and then we're going to look at a number of fluid bed agglomeration examples. In each case, what I'm going to be talking about is what we're trying to do here, how we approach the problem, and why did we choose a particular agglomeration process and the parameters to give us the final results that we're looking for. So let's go through some of these questions and these examples here. So let's start out with an extrusion agglomeration process. I don't have the extrusion agglomeration process down here. I have the high shear because we're actually going to look at both in this particular case. So what we had is we had a customer that came to us. They had a mineral composition, and what they wanted to do is just reduce the dustiness. It wasn't necessary to have, you know, wettability or anything like that. Just get that dustiness under control. So we extruded this thing through one of those screens. We pushed this wet cake through there. It had a binder in it, and you can see the noodles that we formed. Those noodles are about 1 millimeter in diameter and about a centimeter or 2 centimeters long. The product was perfect. We then dried it, and off we went with it. In the meantime, we also looked at a high shear granulation system, and that's what I have down here. This is a high shear granulation system. This is a turbulizer that you can dry in, but you can also granulate in, and we did this in here. And you can see the granule that we made here. There's not a scale on here, but this is about a 400 or 500 micron granule, and it's a very tight granule. It's not that grape cluster. And you're going to get, you know, on high shear mixing, you're going to typically get a tighter granule. But remember, I'm not looking for wettability. I'm looking for dustiness. And you can see the particle size distribution down here. And, you know, looking at the particle and looking at the distribution, or you can see that this process worked very nicely to give us a very tight distribution. So what happened? You know, it worked. It reduced the dustiness. But, you know, this one is truly a what went wrong. That mineral that we used absolutely destroyed the extruder. You know, we ran for about a day and there was no extruder left, the parts. There was an extruder left, but, you know, it destroyed the screen, it destroyed the flights. We had to rebuild the extruder. So even though we had great product and we were rebuilding extruders on a regular basis, it wasn't really a viable process, which is why we shifted to the high shear agglomeration that also worked, but the high shear agglomeration still had an awful lot of wear. So, you know, even though you can do these sometimes, and even though the process really worked very, very nice, I'm not sure that we ever did find exactly the right process. Perhaps from an agglomeration standpoint, we really should have looked at that drum granulation process, less opportunity for wear. That's not what we did, but you know, when thinking about it, we might not have come up with the right process. This product is in production right now. It's still working, but you know, there might be better ways to do it. Let's look at a second extrusion agglomeration. This one was live yeast. So here's what happens with live yeast. We would receive large trucks of live yeast. They're about 20% solids in the truck. We would filter that yeast out to get a wet cake, and that wet cake would then be put into the extruder. So the yeast is still alive. It handles nicely. We're actually making noodles that come out of the system, and it was a beautiful agglomeration process. But you know, the one thing that we didn't do is we didn't add any binder. That's not what the customer wanted. So we then took that granule, that noodle that was formed, and put it to our low temperature drying process. And take a look at the distribution that we have down here after agglomeration. Basically what we have is a peak at about 70 microns. This is the starting material from spray drying, or the starch itself. It wasn't spray dried, excuse me. This is the starting material for live starch. This is the granule. So the question is did we only agglomerate some of it, or during the drying process where it was fluidizing, did it break up? I would say what happened was we had nice viable yeast when this was all done. If we dried it nice and low temperature, but that meant that we had a long time in our fluid bed dryer. The wettability requirements met our customer requirements and dustiness requirements, even though there was a lot of fines in there. But the fact that we didn't have a binder, just meant that we were making great granules, but the strength of the granule was such that it was degrading before we could actually get it into play. Now, it was okay with the customer, and so it was okay with me, but it was a very, very good learning experience, is that you can do something right, and subsequent steps, in this case drying, can actually have a really big deleterious effect. I want to really point out to everybody that this is one of these big issues in drying, in granulation, particularly in fluid beds. You don't want to over fluidize, because that will cause your particle to break up, and you do want to have some sort of binder in there to help you stabilize this whole system together. Well, let's consider this high shear agglomeration process. Here's an example of the high shear agglomeration process that we used. In this case, this is a Forsberg or a Bella mixer. Those paddles in there actually counter rotate, and you form a high shear zone right where the paddles are coming close together. You're actually filling up your chamber with your material. You're adding the binder at that juncture where the particles, where the two blades come together. And in fact, typically you're adding the binder, spraying the binder up from the bottom, not from the top. You can do it either way, but typically from the binder. You can see we were doing a laundry composition. You can see that the particles that we started with, they're chunky, large. We truly have a binder in this case, and you can see that the basically spherical particles. I don't think that we were truly going for spherical, but that's what came out of this. And the distribution of the particles, they were about 500-600 microns. The mode of the particles was there. This was a great process. I mean, it went fast, it went easy, and in fact, with a little teeny system like this is about a 30-liter chamber. If you have an inlet and an outlet, you can almost run this continuously. You can do thousands of pounds an hour with this system. If you have high volume and you have low margins, this is a process to truly consider. From our standpoint, this was one of these wonderful processes. It was an incredibly consistent product, acceptable wettability. Even though it didn't have the grape cluster, there was still enough structure in there to give it a wettability. And currently, it's still in production. It's one of those smilers in the world of agglomeration. Typically, don't have a lot of problems with this process. Well, let's switch to fluid beds. So agglomeration using fluid beds. And I don't have any pictures here to show you, but I have some results. Typically, one of the things in the food industry that's agglomerated a lot is dairy powders. Dairy powders, I mean, they're soluble, but they don't like to be wetted. So people want to make that grape cluster structure as we've seen here. And so the question is how do you do that to get the best dispersibility? You can see here, just as a result, we're just measuring the dispersion times. So the raw material, you take a teaspoon of it and put it in water, and it would sit on the surface for a long time, greater than 90 seconds. Not what we're looking for. If we added the water very, very fast, it didn't improve it. Now, I should be agglomerating in this process, but I was adding the water fast, and we'll come back to what's going on here. If we slowed the water addition down, we made an improvement. And if we slowed it down and added less water, it actually gave us the best result that we were looking for in this particular example. Now, in this case, I'm going to tell you that what we were doing here is at 90 seconds, at a fast water addition, we had very big droplets. The droplets didn't get dispersed out through the liquid, we were actually making big globby clusters at the end that really didn't give us the structure that we were looking at. We were agglomerating, we could definitely see that. It just wasn't a capillary porous structure that was causing this liquid to wet. If we slowed the water down and we kept all the other parameters, the atomization parameters right, we actually started making smaller droplets, and it started to work. Obviously, we were starting to get a real effect on the wettability times. And if we actually slowed it down and added less, we finally got the best that we were able to do. Now, in this particular case, our customer really was just looking for, is this going to have an effect for them? And I think we all knew that it was going to work. The customer knew it was going to work. We knew it was going to work. We just showed them that, yep, you're going to get this good effect with here. And they decided then to bring this in and put an agglomeration in their continuous spray dryer system so they could improve their product. So, good for the customer. They got the information that they needed, and they were able to show, and they probably optimized it again after that to even get it better. Well, let's look at what happens if what we're not trying to do so much is get wettability, but we're trying to control density. In this particular case, we were taking a spray-dried soluble fiber, and you can see the starting material here. It's a typical spray-dried powder, nice and spherical. It was about 50 or 60 microns in size, and we agglomerated it, and what a nice agglomerate. This is the classic grape structure. This is what you're looking for. This should be a nicely wettable powder. That's not what we were looking for. Density control is what we were looking for. And what we found is that we couldn't get it to be consistent. And to this day, we still don't understand why. Now, it's a rate addition. It's a how much time we dry, how we dry. But there was, as this water was added, we were getting a lower density than we wanted, and we were having a hard time getting it to a higher density. The right answer might be that we need to add more water faster, or the right answer might be that we need to, go to a completely different process and not fluid bed. I have a very poor PSD down here that shows you that we really have a nice structure of, if you can see it, it's very light. I apologize for this. 200 or 300 microns, but at the end of the day, this was one of these ones that we haven't completely given up, but we haven't been completely successful either. These are process improvements still being looked at for production. Let's take a look at one of the classic reasons that you agglomerate, to improve the powder flow. In this particular case, what we're looking at is taking yeast. This is not live yeast. This is deactivated yeast, and getting better flow. We want to reduce the dustiness, and we want to make it flow better. So the raw material you can see here from the SCM analysis, has a D50 of about 50 microns. And when we did two different agglomerations, one with water and one with binder, I'm not quite sure why we saw slightly different results here. The binder was a more stable product at the end. Surprise, surprise. We did exactly what we wanted, and you can see here, the structure once again looks like that nice grape cluster structure that we're looking for the agglomerated material. We improved the process. Our customer right now is looking, evaluating this material to see if they want to go forward with it. The problem is it met their requirements, but now does it meet their economics to go with it? On a continuous basis, this process might actually be economical. On a batch process, this is probably not an economical process. So let's consider a different material. This is a spray-dried protein, and they were looking to improve powder flow. And so we picked a fluid bed drying. That was a right process to look at. And we found that we could agglomerate it. So it always depends on which do you start with. Do you start with looking at the SCM of your product or your raw materials in your product, or you look at the particle size distribution? In our case, we looked at the particle size distribution. So we have a spray dried product that's about 50, 60 microns in size with a broad distribution. And we ended up agglomerating it to a pretty good single peak at about 400 microns with some unagglomerated material here. Now let's take a look at this. This is one of the reasons that, in most particle processes, and particularly in agglomeration, you really just don't want to look at one characterization method. Particle size is a great one, tells you something's happened, but let's take a look at the SCMs of these, the starting materials and the agglomerated materials, because there's a lot to see here. To start with, this starting material is not a typical spray dried material. It looks like it's broken glass. This is just astounding to me that you can see that it looks like shards, that this is a hollow particles that must be very, very fragile particles. Now that's going to have a different effect on how it agglomerates, how it fluidizes, and how it truly processes. When we agglomerated this stuff, you can see the agglomerated particle here, and in one sense, you can say you did make that cluster that you were looking for that wettability. And that's true, but let's take a little bit closer look, particularly up at the top of the screen. You see how it's kind of rubbed out? What's happened is there's been enough water that's been added to this system that we dissolve significant amounts of this protein and then dried it into not the grape clusters held together by these solid bridges, but it looks like it's kind of, we're forming a new structure almost altogether. This is an indication, I mean, it improved the wettability. A customer was happy with this, but this is an indication that the water addition is too fast, or the droplet size is too big, or the drying process isn't lined out exactly. So, there's a real learning here that, it might not have made any difference what the starting material looked like. It was just remarkable to me what it looked like. But the ending structure here tells me something about how good I'm doing. In later experiments, we went back and lowered the water rate and changed the atomization to get a better looking product. But I thought it was very illustrative what's going on here and what's going on. So, it flowed better, it dissolved better. They took the process in-house, but that globby structure, is really an indication that you're not quite on your game 100%, and you need to control your process conditions. So let's consider what happens with 3 different samples where we're looking at drink additives, and we're looking specifically at wettability. So all of these materials are highly soluble. They're all about starting materials. These are the pictures that you're seeing up here are the agglomerates. They're all about, the starting materials are all about 70 to 80 microns in size, but some of them are multi-component and some of them are single component materials. So this is a good technique for making your powder wettable and getting all the same constitutive particles in one particle, so you have a uniform dosage, if you want to call it that, when you're making a drink. What I found incredibly interesting about this is that the structures are completely different. The process parameters were done about the same, so there's a real functionality here of the starting material and what's going to happen. If we look up into the upper right-hand corner here, you can see that the grape cluster structure that we're looking for, that's good, that's what we want. It seemed to be okay. I can see that there's a little bit of, looks like there's flowability on this, or the particles have kind of smoothed out, an indication of adding too much water too fast, or the droplet size are too big. But look at these 2 particles down here. These are blobs. It met the requirement. It was still wet enough, and I think it's because there was enough surface structure on here to give wettability, but it didn't have the wettability that it could have had, and it made a denser product because we took a lot of that porous structure out of there. So, the answer was I got wettability and I got density. Maybe that was good. Up here, I got wettability and I didn't get density. Maybe that was good. So it depends on what your customer wants and how it's going to operate. I think that all of these samples could have been made to have better wettability by making more of that grape cluster structure, but I think the final product would have been it would have been weaker, and we could have seen more fines in a case like this. I have one last example here. This is a fluid bed agglomeration of protein, and we've talked about a protein in the past, but this one had really a special starting material attribute. It had an incredibly low density. We just don't see this type of low density unless you're looking at glass bubbles. But this one, the customer was looking for this to be agglomerated, so we put it in our fluid bed agglomerator, and we started spraying on this thing. And what happened was the material agglomerated and the bed expanded about 5 times what it was to start with. And that's what the little schematic was to show you down here. Now, typically we don't spray from the top. Typically we like to get into the fluid bed. But this one, I'm not sure why we set it up, but the results were remarkable. Number one, this product formed this incredibly lightweight material. So if the bulk density to start with was 0.079, it was probably down to 0.02. It filled up the bed and it stopped fluidizing. And what happened is we couldn't shut the atomizer off fast enough. And now this stuff that wasn't being fluidized was getting sprayed on by a continuous stream of water. It turned it into mush. It was one of those incredibly interesting, what the heck happened here? And we were able to get some powders out, because I'm going to show them to you in a second, but it wasn't an easy process to look at. So let's just take a look at what this looked like. The starting material was a little bit bigger than we normally get, and you can see it is a spray dried material. And if you look closely at it, the structure of the particles here will really indicate that these are hollow, which would help explain the low density that we started with. But if you look over here after we agglomerated and we're actually able to get some of this structure out of here, you can see that this is absolutely a classic grape cluster. What you're looking for to have that wettability, low density, it's got everything for it. In fact, it's such a low density, it filled up the dryer or the agglomeration system, and we really couldn't process it in a commercial sense. So what went on here? I think this is a classic case of that low density powder had the ability to stick so easily to each other. It didn't have enough inertia to break when a liquid bridge was formed. There wasn't enough inertia to break it. And so you just formed this rapidly low density structure. It's a beautiful structure. Don't know how to scale it up. Maybe a continuous fluid bed would do it, but the density is so low you couldn't put enough in a bag to make it worthwhile. The whole aspect here of the examples that I've given you on water rates, on densities of materials, on whether it's a flow or a dense granule or all these aspects really play a part, and you really have to be on your game. So let me give you some things that I left out. I can't do everything in a talk like this, but I didn't talk enough about pharmaceutical agglomeration. I apologize. That's not my field. I will tell you that many of the considerations, the water addition rate, the densities, do I use a high shear versus a fluid bed? The things that I talked about should be very applicable to pharmaceutical agglomeration. You'll just have to kind of change the materials to fit the purpose. I didn't talk about tabulating and briquetting. I mean, these are two other techniques that are really important in the agglomeration. I just didn't have time to do that. And I didn't talk about batch versus continuous, not just fluid beds, but batch versus continuous agglomeration process. I didn't talk about using a spray dryer as not only a spray dryer, but in combination with a fluid bed, or actually doing an agglomerating spray dryer. These are very critical agglomeration techniques. And I talked a little bit about process conditions, but we could spend hours talking about process conditions and the theories behind that. But let me tell you where you can get some of this information. You can always call us, please do. We love to talk about agglomeration. We might not have all the examples or all the answers, but I would highly suggest you consider looking at IFRI, the International Fine Particle Research Institute. I'm president of that organization. It's an industrial consortium. It's a great organization. They've done an incredible amount of funding of agglomeration understanding. Many people have been funded doing this. Currently, we're funding a woman named Rachel Smith at University of Sheffield. I would highly recommend, if you're in Europe, to contact her if you have some consultant issues. Here in the United States, Paul Mort used to be working for Procter & Gamble, but recently, maybe 3-4 years, has moved on to Purdue University. He's an excellent consultant and an excellent expert in this area. Obviously, you know, the people that make the equipment, and I've only listed fluid beds here, but you know, the IREX, the Vectors, the Glass, the GEAs, all these people that make these, the people that make the Bella mixers, all these people that are making these high shear or fluid bed granulation, these are a wealth of information. And if you really want the Bible to look at, you know, have a reference book on your desk, the book by Jim Litzter and Brian Ennis, which I've copied here. This is the book that we go to. It really has a lot more of the mathematics and, you know, the details that you need to understand. I think there's lots of resources out there, and if you need help, you know, give us a call or call one of these people or talk to me about becoming a member of IFPRI, because you'll certainly get your fill of some leading experts talking about agglomeration in those areas. So ending up, you know, I would say that agglomeration, lots of advantages for doing this. I mean, there's a functionality, there's you know, whether it's a wettability or a density or a flow, these are incredible technique for changing all these processes. You have many processing options. I talked about 3 today. I mentioned 4 or 5 others. You know, there's much to consider in this area. I cannot stress how important the process conditions and materials, how critical they are to getting the right product that you want. It's an incredible matrix that has to be kind of peeled back and then continually monitored. And the way that you monitor it is by analysis. If you are taking too many particle size distributions or too many SEMs or optical images or wettability studies, I don't believe it. You can't analyze too much, and the way that you're going to be successful in this area is understand the fundamentals. Read Lister's book, call us up, or analyze the heck out of what you're doing. Thank you all for listening. I really appreciate it, and I think we probably have some time for a few questions.
We do, and thank you so much, Willie. So when you were speaking, this question came up. How do we identify if we have achieved a high shear effect?
Whoa, oh, jeez. How do you identify if you've achieved a high shear effect?
Quantifiably.
You know, I don't actually know. That's a great question. Give me the stumper right to start with, for God's sakes. You know, I think you can do some powder flow measurements. You know, some Genicky shear cell to try to see what's going on. Obviously, the FT4 is a method that you can put some high shear into. I think you would actually go to some powder rheology, but you know, I'm thinking of a high shear and a high shear granulator. Do you really have it? I think, you know, maybe from a just a practical standpoint, are you getting granules? That's maybe not what you want to hear, but that's a great question, and I'm stumped right from the start.
The next question is, what about agglomeration in slurries?
Agglomeration of slurries. Well, that's kind of what you know, a slurry. Wow. So 2 things that we can talk about. Is the slurry just a wet cake, or is the slurry a flowable slurry? Let's talk about it in 2 ways. When we did the agglomeration of the yeast, we actually made a paste that had enough viscosity to actually push through an extruder. If you have a true slurry, you know, you have particles in suspension, a stable suspension. The way that you agglomerate it, we don't call it agglomeration, we'll call it flocculation. You can change the pH is one way to do it, or you can change the pH, or you can change adding some binders, some flocculants that will actually cause this to flocculate. Slightly different process than the dry agglomeration that we're talking about. But people look up the term flocculation. That'll be the right place to go for a slurry agglomeration.
Thank you. And this person is new to particle mixing, so he or she is wondering if you could offer a definition for wettability with respect to granulation.
There people do actually have that. There's once again in the Litster book, you can actually find that information. There's actually terms for how much water is in the system and where it gets to a point that it's appropriate for agglomeration versus not. But my suggestion would be to take a look in that. If you can't find it, please give me a call.
Can you please speak about the morphological effects of different agglomeration techniques?
So I tried to make the point, and perhaps not well enough. Fluid beds are going to typically give you a more open structure, which is it's more of that grape cluster structure. High shear granulation is going to give you more of a closed structure. And so depending on if you want a lower density, fluid bed might be the right way. If you want a higher density, the high shear methods. And if you actually look at the compaction methods, it would even be higher shear, or excuse me, density. So, I would say that, your highest density is going to come in compaction, briquetting, calcination. The lower density is going to come in your fluid bed.
Thank you. Next question. You show a relatively spherical agglomerate from high shear granulation. What would you say the applicability of the high shear granulation is for spherical agglomeration?
Well, that's an interesting question, because high shear agglomeration is a technique, and there's another technique called is a way of making an agglomerate. People use a technique called momerizing or spheronization, where you're actually tumbling particles and you're causing it to make spheres purposely. Whereas the high shear agglomeration, in that case, it was pretty spherical, but it wasn't necessarily what we intended, but it was what came out. But if you really want to make it spherical, get a momerizer or a spheronization, and you can get that sort of structure.
Okay. The next question is, my question is kind of contradictory. How can we avoid agglomeration?
How can we avoid agglomeration?
Right.
So typically what you'll do, you want to put something in there to keep the particles from coming together. This is a different talk. I mean, I like this one also. Typically when you want to make powders flow better without agglomeration, you put flow aids in. And flow aids are typically small amounts of fumed silica that act as kind of standoff particles that keep things from agglomerating. That would be the first, not knowing exactly what your application is, I would start with a little bit of fumed silica, and if that doesn't work, maybe we should talk.
Thank you. Now the next question, really, I can see that this is coming from a pharma, a person from the pharma background. Laser diffraction measurements of needle-like particle 10:1 aspect ratio. Can you comment a little bit more about that?
That's always the challenge, because laser diffraction techniques, typically assume a sphere, so they push everything into a sphere. The best I think that people see with the laser diffraction system is, a bimodal distribution, even though they might have just needles, and so they'll, looking at the long end versus the long ways, lengthways versus end on, you'll get two different particle sizes. In a case like that, I think there are techniques that might be better for it, but I would always be looking at an SEM to do some analysis. And there are some techniques that will do image analysis of your particles. I'm not sure. A cam sizer is one of the techniques, but HORIBA might have a technique also for this, where you're actually measuring and looking at aspect ratios. So, you're probably not going to get it by the laser diffraction method. You're going to get it by an optical observation method.
I agree. I think typically 5-to-1 ratio is when you begin to see bimodal distribution, so that larger peak isn't necessarily agglomeration. So we have the PSA 300 automated microscopy that may be more fitting for pharma people who are looking at smaller particles than the range that the cam sizer offers. But I'll move on to the next question. So feel free to email us again, either at labinfo@horiba.com. Last question is, please, can you talk a little bit about the surface energy and agglomeration during micronization?
Surface energy and so well, that's a
Loaded.
that is a loaded question. I mean, one of the things that people see as a limit to grinding, Wolfgang Peukert and others have really studied this effect quite a bit. As you grind down, if you're not stabilizing that surface, you reach a point where it's called the limit of grinding, and you just can't seem to grind any farther because you're grinding and agglomerating at the same time. The addition of appropriate surfactants or liquids can actually push that limit of grinding down. But this is something I would highly recommend that you look at. Some of the work that Wolfgang Peukert has done and others in this area will get you to that limit of grinding and allow you to push that limit down quite a ways.
Well, thank you so much, Willie. I know we're a little bit past the time, but we didn't finish asking all the questions just like other webinars that you did. For those people who didn't get to have their questions answered, please feel free to email us at labinfo@horiba.com on behalf of our group. Thank you so much for attending, and we'll hopefully see you at the next webinar on nanobubbles. Willie, thank you so much. Bye now.